Hello everyone, this is Sherif Abdelmohsen and Ahmed Hassab presenting the paper titled A Computational Approach for the Mass Customization of Materially Informed Double Curve Facade Panels. We are from the Design, Computing and Fabrication Group in the Building Sciences Lab in the American University in Cairo in Egypt. The problem in this paper is related to the fact that most approaches to enable mass customization of double curve facade panels like cold bending, forming, robotic milling and the like still have some challenges for including waste reduction, accuracy, surface continuity, and mostly workflow disintegration for different materials and processes, leading typically to a waste in resources and materials. So our approach is a computational approach for the design and fabrication of materially informed double curve facade panels with complex geometry, focusing on generating customizable double curve panels with complex geometry using Rhino and Grasshopper with different material properties, optimizing fabrication workflow, where waste material is reduced compared to other conventional workflows, applying these workflows to 4 different fabrication techniques as will be described, and producing optimized and accurate double curve panel prototypes based on different materials such as acrylic, clay, and medium density fibers. Our first experiment is with vacuum forming, which is typically the process of heating a thermoplastic material and shaping it in a mold, where a sheet of plastic is heated to a forming temperature, stretched onto a single surface mold, and forced against the mold by vacuum. Most previous attempts to vacuum forming with double curved facades have faced some challenges related to surface congruity, precision, waste reduction, and some economical challenges. So our approach couples multi-point forming together with automated free-form material deposition to create mass-adjustable double curve facade panels. We developed this vacuum forming simulation workflow using a script in Grasshopper, where we rationalize acrylic panel surfaces and extract z-values for fabrication. The inputs for this were the double curved surface to be fabricated, the number of subsurfaces in the U and V direction, the number of rods in the U direction and V direction. The main outputs included the selected item for data extraction, the double curved surface and its projection on the XY plane, the travel distances that the rods will move in the Z direction to push the acrylic sheets to a specific location on the new surface 3D location. We also developed a vacuum forming machine where a cast silicon sheet connecting a set of vertically displaced metal rods regulates the desired geometry of the heated acrylic panel via vacuum forming. The fabrication process using this machine involved casting the silicon sheet based on the dimensions of the machine workspace, sending Z coordinates to the adjustable mold, preparing an acrylic tile to be heated in the oven till it reaches elasticity, loading the sheet on the adjustable mold and closing the machine using the fabric, initiating the vacuum process and repeating the same with the remaining tiles. The figure here shows the vacuum forming device based on multi-point forming and material deposition and the fabricated acrylic tiles. The second experiment, which relates to clay deposition, a script was developed here to deposit subsequent vertical layers of clay using an extruder attached to a CNC machine. We defined basic curve components, identified Z directions for form expansion, defined vertical movement components, area components to define the center of base curves, a loft form for surface printing, and the rotation definition for vertical surface curvature along the rotation axis. The surface was then rationalized and its fabrication printing path for the CNC router was prepared. This involved dividing the base curves, defining the printing path curve, and defining the movement vector to follow the path connected to the CNC. Another script was developed to simulate the clay printing process, including modifiers to the CNC router and deconstructing the vector to synchronize the movement and transferred movement in X and Y and Z directions to the machine head. These figures show the model surface, also the components of the setup, including air pressure, flow, extruder, CNC motor, clay mixture container, and it shows the simulation preview for clay deposition experiment, and on the very right, the extruder device added to the CNC router. The third experiment related to sectioning, which is generally a method of profiling components, typically in relation to surface geometry by means of a series of sectional cuts through a digital model. We defined a workflow script in Grasshopper to rationalize polysurfaces, prepare planar cuts for the fabrication of MDF sheets, and apply the desired angle of sectioning technique and define an optimized method for the assembly for the resulting complex double curved geometry. The objective here was to generate a double curved surface using a planar material, simulate its fabrication process, and increase the accuracy of the generated surfaces by linking extracted data directly to the CNC router. We used 14mm MDF planar sheets and vertical metal rods for stiffness. A surface was first created on a sweep and was converted to a polysurface, which was then rationalized and prepared for fabrication using the Grasshopper script. The inputs for the script were the polysurfaces, the material thickness, the metal rod coordinates in both X and Y, the grid size for arranging planar cuts, and coordinate tags in X and Y as well. The outputs included the 2D geometry for CNC subtractive fabrication, the number and position tagging for the fabrication, engraving, cutting, and simulation. The figures here show the outputs of the sectioning process, the process of rationalization of the polysurfaces, and preparing planar cuts for fabrication on the left using the sectioning plugin for a vertical sectioning process, and on the right is the fabrication or the fabricated outcome at the very end. The tessellation experiment, of course, tessellation describes a collection of pieces that fit together without gaps to form plane or surface. It can represent, in essence, any shape as long as they fit together in a tight formation. In this experiment, the objective was to generate a double curved surface using metals and increase the accuracy of the surface using tessellation as a technique while linking the extracted data directly to the CNC router. The script was developed to define and control the resolution and number of multidimensional and directional subdivisions of the desired metal sheet surface, surface depth, surface tagging, tile assembly, cut sheet geometry, and also vertical and horizontal assembly. The inputs for this process were the double curved surface to be fabricated, a mesh surface component that converts rhino NURBS to a mesh surface to induce the basic surface tessellation, and the number of subdivisions in the U and V direction, the tab depth used to lock the tiles together, and the outputs included the geometric component representing the tessellated mesh, tagging of the tessellated mesh panels, output curves, panel and tab tagging, and control of the diameter for pin cuts. The core component of the script also included subcomponents for 3D mesh assembly to represent 3D surface upon tessellation, 3D face center to represent the numbering annotation, and mesh tile outlines and inner edge mesh tiles, and also centroids for pin cuts. The plugin was applied to the surface and the CAD fabrication file was extracted. The panels were then folded for tighter assembly. The figure here shows an automated surface tessellation and fabrication tagging of the double curved surface using tessellation Grasshopper script developed. And here on the left is the script output showing surface tags and 2D cutting sheets for panels. On the right is the 2D cutting sheets showing the 3D assembly, panel engraved boundaries, and on the bottom the cuts for connection pins. As a general discussion for all the experiments, the objective was primarily, as mentioned at the beginning, the efficient and accurate representation of double curved surface geometry data extracted for fabrication based on a variety of materials. So we had 4 materials and 4 techniques, including the materials acrylic, clay, MDF, and metal. The purpose of the scripts was to streamline and partially automate the process of data extraction for fabrication on double curved surfaces while considering all the material properties and configurations. For the vacuum forming experiment, the implemented device increased the accuracy of the total double curve geometry in comparison to conventional vacuum forming devices. Also based on a preliminary comparison to different thicknesses, the thickness of the sheets used here was 2 millimeters, which allowed for quick elasticity of 50 seconds under 200 degrees Celsius, allowed for a more faster and more reliable fabrication process. The experiment was also originally implemented using 9 metal rods for easy manipulation. By increasing the density of the rods from 4 to 16 rods, it was observed that the surface resolution was further increased by 200% upon doubling the number of rods. For the clay deposition experiment, here it was a low-cost approach where a 3D clay extruder was developed and attached to a CNC router. Also, the local materials and clay mixture were purchased from a local provider. The CNC machine, in addition to developing a script to simulate the double curved vertical surface printing process, the machine was used effectively for a sequential additive manufacturing process by automatically linking data extracted from the double curved geometry of the model to the material deposition in the attached extruder. Also, as opposed to more sophisticated methods such as robotic fabrication and deposition using extrude tool heads, this approach utilized the conventional router machine for economic reasons and to also preserve surface continuity and precision while minimizing waste, where the double curved geometry data was linked directly to the pumping and deposition mechanism of the extruder. In the sectioning experiment, as opposed to tools like Slicer for Autodesk Fusion 3D60 or Rhino Nest, which have the capability to slice and convert 3D models into 2D patterns that can be cut out of any flat material, the added value here was the ability to directly extract fabrication data, simulate the sectioning process, and identify accurately the location of any vertical or horizontal structural stiffening, as in the metal rods described in the experiment. This allowed for an element of structural integrity, also in addition to reducing preparation time and enhancing the accuracy of the fabricated model. It was observed from the experiment that the number of sectional cuts was directly proportional to surface resolution and accuracy, while the layer thickness was inversely proportional. In the tessellation experiment, also as opposed to a method like Rhino Nest, prefabrication nesting and optimization, the added value here was the direct extraction of the required data for fabrication and simulating the tessellation technique as well as the assembly process for metal double curved panels. It was also observed that the surface resolution and accuracy was almost 200% upon doubling the number of surface UV subdivisions. As a conclusion, as we said, we introduced a computational approach for the design and fabrication of double curved facade panels with complex geometry, different material configurations, while focusing on optimized workflow and waste reduction. The scripts were developed using Grasshopper to apply surface rationalization and optimization, automated data extraction for fabrication, and simulation of fabrication process for all the 4 techniques described. We demonstrated that the approach can further achieve higher levels of surface resolution and reduced waste material per type and surface complexity. Thank you so much.